Yes, absolutely. She's very smart. Transformation of natural gas into hydrogen. In fact, the vast majority of hydrogen in the world used for commercial operation are produced by reforming method. And what we interestingly see that along with methane, I also produce CO2. That goes against the an idea that hydrogen is a very clean fuel, no global warming. But as you can see, every hydrogen molecule produced is associated with the release of greenhouse gas, let alone other things. So anyway, this is what gasification is. So this afternoon I'll first explain the different types of gasifier and comparison of different types, and go into the theory of gasification, what goes inside the gasifier, and with specific reference to biomass. I have to make specific reference to biomass because Professor Farid otherwise will not pay my hotel bills. It has to be biomass. And then finally, I will show you a step-by-step method for design of gasifier and the design methodology. So I know that the first class after lunch is always a very boring class. So I'll show you a short movie to get you started so that you can wake up.
Hey everybody, this is Ben from Victor Gasworks. How are you doing today? I'd like to thank you for stopping by and learning more about gasification. I've been getting a lot of the same questions over and over on gasification. I really wanted to answer them, so I put together this Gasification 101 video series. It's going to be multi-week, and it's going to take you through a lot of the basics of gasification, because there's a lot of upside here, but there are some challenges as well, and it's good to get everybody's expectation level and knowledge on the same kind of platform. Now, what I really envisioned with Victor Gasworks is having it as an open source gasification community where people can come together and test different aspects of the gasification equation and bring that knowledge back to one centralized place where we can all enjoy it. Because I know right now there's a lot of gasifier enthusiasts who are just replicating each other's work unknowingly. We're all reinventing the wheel, and that's really an inefficient way of doing it. And I think we have a lot more fun, a lot more progress if we pool our resources. So I'd like to get everybody on the same page so we can do just that. So here's some of the things we're going to learn during Gasification 101. First, what is gasification and how does pyrolysis work?
How do I get my
solids
concept
fuels
here?
into gaseous fuels.
How much is the
We're going to
concept
talk
from
about
there
what
to here?
gasification can do for you, transport, electricity, even solar methods. And then there's also the challenges posed by gasification. We have to worry about tar, moisture, and fuel sensitivity. Then we're going to talk about the history of gasification. This is not a new technology. This is actually old technology that was implemented heavily in Europe during World War II.
And
Next, we're going to look at the
full screen and go to the Thank you. Finally, yes.
Hey everybody, this is Ben.
This is a very, very broad
How are you doing
overview
today?
of the
I'd like
process.
to thank you for stopping by and learning more about gasification. Now, I've been getting a lot of the same questions over and over on gasification. I really wanted to answer them, so I put together this Gasification 101 video series. It's going to be multi-week, and it's going to take you through a lot of the basics of gasification, because there's a lot of upside here, but there are some challenges as well, and it's good to get everybody's expectation level and knowledge on the same kind of platform. Now, what I really envisioned with Victor Gas Works is having it as an open source gasification community where people can come together and test different aspects of the gasification equation and bring that knowledge back to one centralized place where we can all enjoy it. Because I know right now there's a lot of gasifier enthusiasts who are just replicating each other's work unknowingly. We're all reinventing the wheel, and that's really an inefficient way of doing it. And I think we have a lot more fun and a lot more progress if we pool our resources. Everybody on the same page, we can do just that.
So here's some of the things we're going to learn during Gasification 101. First, what is gasification and how does pyrolysis work? And how do you turn solid fuels into gaseous fuels? Then we're going to talk about what gasification can do for you, transport, electricity, even soil methods. And then there's also the challenges posed by gasification. We have to worry about tar, moisture, and fuel sensitivity. Then we're going to talk about the history of gasification. This is not a new technology. This is actually an old technology that was implemented heavily in Europe during World War II. And next, we're going to look at the energy picture. I'm going to show you why gasification is such a vital part of this. And of course, there's an environmental impact to everything. We're going to look at the environmental impact of biomass energy. We're going to follow that with all the different types of gasifiers. These are your cross-draft, your downdraft, your updraft, and whatnot. Then we're going to get into popular designs like the Ember. And finally, gasifier operation. Learn how to operate a gasifier properly. Then I'm going to cover the 5 key components to successful gasification. You have to get all your ducks in a row if you want this to work well for you. And all those opportunities are going to lead you to a lot of different paths. So we're going to talk about the different paths you can take with gasification. Next, we're going to talk about the economic impact because we're creating industries here with this new energy source. And we're going to talk about what the future holds for gasification and green energy in general. And finally, we're going to wrap up with some resources. And then finally, we're going to finish up with a big announcement, something that's going to make your gasification work a lot easier. So look forward to that.
Before we talk about what gasification is, let's talk about what it isn't. It isn't anaerobic digestion. It isn't shoveling shit into a hole and waiting 30 days for it to make methane, because that's kind of gross. We have politicians that shovel enough shit for us. What gasification is a thermal process that takes dry solid fuels like wood and biomass and converts them into the more basic elements. And as those basic elements come back together, they form a gaseous fuel called syngas or producer gas. Compared to burning wood and only getting heat, when we create producer gas, through gasification, we're making a fuel that we can use for fuel cells, burners, and engines. And it's a much more efficient way of turning biomass into energy.
Theoretically, any biomass can be gasified, but practically there's no one apparent design that can gasify every biomass fuel efficiently. You see, every feedstock has its own characteristics, much like the liquid fuel we use in our cars to power our different engine designs. What's so cool about gasification is that it's extracting energy from the sun, much like most other energy sources, but it's doing it after the plants have used the sun's energy to grow, fruit, purify the water, and release clean air. Try getting all of that out of a solar panel. You can't. Those seldom appreciated natural processes are priceless.
All right, so let's take a look at a gasifier. This is an industrial-sized GEC. And what most gasifiers consist of are a vessel within a larger vessel. Now, the first vessel is where you keep your biomass, where you start the hearth reaction down below. And then you keep it within the second vessel because it's going to come out of the hearth, and then it's going to travel between the walls of these 2 vessels until it gets to the exhaust port. In order for gasification to take place, 3 things have to happen. First, air is pulled into the unit, and it gets down to that little hearth area, and it starts a partial combustion process. That partial combustion releases heat that works its way up into the biomass, and that starts pyrolysis. Pyro meaning fire, lysis meaning broken down. So this area is broken down by the heat, but it's a low oxygen environment because the air is going to be pulled in and then sucked down, and then it's going to go out and then circle around until it comes out the gas outlet. So you have air coming in, going in, it's partially combusted, releasing pyrolysis. This has turned this into tarry vapors, and those tarry vapors are going to get pulled down through this area called the reduction zone, and it's going to consume most of the tars, and it's going to rearrange all the molecules so you have producer gas when you're done. And that gas is going to flow out, and then it's going to go to our cleaning system, but we'll try to purify it for use in an engine or a burner. You can actually conduct your own little experiment in pyrolysis right now. Go get a match and light it, and what you're going to see is that it's not actually the wood that's burning, but it's rather the gases exiting the wood that are burning. And that's exactly what's happening in pyrolysis. So let's recap. Gasification unlocks the fuel potential of dry solid biomass. And gasification needs three things to happen: combustion, pyrolysis, and reduction. And coming later this week, look for Module 2, What Can Gasification Do For You? And Module 3, Challenges of Gasification.
Okay, go back to our original desktop. Sorry about the hiccup. So there are three main types of gasifier, as you can see here. Moving bed, fluidized bed, and chain bed. And as you can see that each of them has a different range of temperature. Moving bed, somewhere in the range of 700 to 1200. Fluidized bed always less than 900. And enchained bed in and around 1500 degrees Celsius. And what is important to note here, that all these types are not applicable for all sizes. Enchained bed typically used for higher than 100 megawatt. Fluidized bed in the range of 10 to 100 megawatt thermal. And moving bed less than 20 megawatt thermal, and co-current is less than 5 megawatt. So these are used generally for small scale application. This is medium scale and large scale. We'll go more into that. But let's take another critical look of different aspects. So moving bed that I talked about is made of these three types: updraft, downdraft, and cross draft. And here, the important characteristics that in updraft you have a high tar content, downdraft has a very low tar content. And I was talking to some of you here who is working on downdraft, and those units are typically used to run diesel engine because that cannot tolerate much of a tar. So this is extremely high. And also that in the engine flow, the tar is also very high for very different reasons. In terms of particulate or ash, the cross draft is a very high particulate in the gas. And updraft, good, downdraft, moderate. But fluidized bed has very high ash content. So you got to be careful when you use fluidized bed gasifier for that kind of application. And engine flow is also very high particulate for the simple reason that entire ash goes with the gas. But one good thing is that some variation of this engine flow gasifier, this ash is molten, so the reason separated. Now let's look at what kind of feedstock we use. Now, of different types, we can see the fluid bed has the maximum flexibility in terms of fuel. In the video, we saw that they were saying that theoretically all gas biomass can be converted into gas, but in practice that is not the case. But if I use fluid bed, it can practically gasify all types. And then downward gap, unfortunately, though it is very good, low torque, but it's highly specific to the type of fuel you are using. You change the fuel, the performance changes entirely. Whereas updraft and crossdraft has moderate tolerance to the variation of the feed. Now, in terms of mixed fuel, fluid bed has an excellent response to mixed fuel. That means if I want to burn a variety of fuels, same is the case for engine flow, but updraft, downdraft, crossdraft, they are very poor in those things. Now let's look at the size, how important the size is. Updraft, very good size flexibility. No, actually, this author who got this 18 did it wrong. I tell you why. Updraft doesn't have a good size flexibility. It's limited. This bubbling, the fluid bed has a fairly good tolerance. Again, this author was wrong in saying fair. Size is very important for engine flow. I tell you that why I say this wrong. Few years back, we were working with a multinational company who had an updraft gasifier in a tire factory in Vietnam. This updraft gasifier is so sensitive to the size of the fuel. The coal they use, they have to spin it, double spin it, which means they take out the large size and they take out the small size also. As a result of that, they had a fairly large amount of fuel, coal, which has no use in the gasifier. So they had to go for another process where they could have to pelletize the fine coal and then feed it. So that's the reason that that company got us to design the fluid bed gasifier for them. So this author is wrong. It is not correct. So anyway, so we can see that different gasifiers have different characteristics. Another important thing you may like to know, the updraft gasifier has a very low exit temperature, which means it has a very high thermal efficiency. Because here, I'll show you later, the gas passes through the drying zone. Whereas downdraft and crossdraft, this gas exits directly to the gasification zone. The temperature is very high. The same thing for bubbling and saturating, and engine flow is also very high. So all of these are, from thermal energy utilization standpoint, are not very efficient. Here is another comparison of different types. Okay. In fixed bed, there is downdraft, updraft, crossdraft. Downdraft, they produce low heating value fuel, moderate particulate, and very low torque. That's a major characteristic of downdraft. But whereas updraft produce flue gas of high heating value, but high level of torque. And if you go to the fluid bed, we can see that it has a higher efficiency than some of them and produce higher heating value fuel gas. But most important feature of this is its fuel flexibility, and it is used for medium scale application. And then the indirect gasification. Indirect gasification is very rarely used in industry. That's only theoretically possible. So let's take a closer look at the moving bed. We'll discuss updraft, downdraft, and crossdraft. Here is a schematic of an updraft gasifier. Now please make a note that typically for biomass they design for a great inventory or great throughput of 150 kilogram per meter square per hour of dry biomass. This great processing area is based on superficial velocity of gas into the system. The product gas is rich in tar, and we typically use maximum size of 3 to 4 meter diameter, not more than that. And thermal region, which I will explain later on, 3 to 4. This is very good for direct use of gas in the combustor because gas temperature is 800 degrees Celsius. So in the particular industry that we were working, tile industry, where you fire the gas directly into the kiln to have a high temperature, 1000 degrees Celsius or 12 degrees Celsius. So it is very convenient that we get that they were getting steam gas at 800 degrees Celsius. They are cleaning it and directly taking the furnace. So that is very useful. Now, this is the updraft gasifier. Why we call it updraft? Because the gasification medium comes from the bottom and it moves up to the different chamber, different region, and then comes out here. Updraft gasifier. The pyrolysis, downward gasifier, where it comes from here on the sides and flows down to the combustion zone, reduction zone, and then out. Now, as it was explained in the video, this region which receives heat from the combustion zone, that helps decompose the biomass into the pyrolysis compound, and then some of this compound they burn here, and the char that comes out drops here. They are reduced in this zone, which is gasification zone, because all the oxygen which is fed here has already been consumed in the combustion zone here. So you have the hot gas passing through here. The very fact that tar is mostly produced in the pyrolysis zone passes to the hot combustion zone, they are all tar is cracked. So that's why you have a very low tar content here. Now, this is cross-draft gasifier, where air is passed from the side, and this is the different zone, and hot gas passes from here. But this is a very, very limited use. It is mostly for theoretical interest. So, going back to this different types, we now look at fluid bed. The question is, why fluid bed? The major motivation of using fluid bed is fuel flexibility, particularly for biomass. Biomass is often mixed with different things, and also waste product. Biomass waste product is a mixture of all different fuels. So that's why fluid gasifier is very useful for gasification of biomass. And it operates at low temperature, relatively low temperature, which reduces maintenance cost and operates in downturn. But it is cost effective in industrial scale, 100 to 400 megawatt thermal. But I would qualify this statement because Generally, that it is less than 100 megawatt, but only you guys have a pseudo fluidized bed gasifier, which is about 400 megawatt capacity. This is the fluidized bed gasification system, and so maximum capacity, the factory assemble up to 3 meter diameter are available, but we can go for a larger capacity that requires site construction. And this typically operates under thermal region 2 and 3. The the tar is an important thing to worry about, but we can use olivine catalytic bed material to crack to a certain extent, but not a whole lot. So if I look at the temperature distribution along the height of the fluidized bed, it will look something like this. The sharp rise to the temperature, which is fixed, which rises, and then it drops in the upper region. So interestingly, fluidized bed is the first, fluidized bed gasifier is the first application of fluidized bed in commercial scale. That was done by Winkler in Germany. This was the original German patent diagram of Winkler gasifier. So the recent past, there is another type of fluidized bed gasifier coming to the market, is circulating fluidized bed, and that is a different operation. Now, so I do not, let me see, I don't think I have, I'm sorry, I do not have here this view of the engine-flow gasifier, which I showed this morning, which essentially that is a burner tank to inject finely ground coal with the oxygen and burns a sort of tunnel like furnace. In addition to these commercial scale units, there are also 3 novel types which are in research stage, not applied in industry. Supercritical water gasification, chemical looping gasification, and plasma gasification. To supercritical water gasification, as the name suggests, that operates in the above the critical point of water, which is 22 megapascal, 374 degrees Celsius. And I will explain this one briefly. Let me see if I have a diagram for this. No, I don't have a diagram for this now. Chemical looping gasification is a novel technology to produce relatively pure carbon dioxide and relatively pure hydrogen in the same system by using limestone as a medium. I'll show you. I have that figure in another presentation, which I showed this morning. So, Gasification medium passes through this solids in which biomass is fed and calcium oxide is fed. So, in this process, the calcium oxide absorbs the CO2 which is produced in gasification reaction, forming calcium carbonate. Now, I gather many of you are chemical engineers, so you know that chemical equilibrium. A gasification reaction produces CO2. And if the CO2 is removed continuously as they're produced for the reaction site, obviously forward speed of the reaction is faster. So we have a high equilibrium concentration of carbon monoxide, methane, and hydrogen. So this calcium carbonate comes here. And here we add here or other medium to calcine calcium carbonate. And this heat for this endothermic reaction is provided by the combustion of charge. And this calcium oxide, which is produced here, is fed here, and then from this in our laboratory we did some work on this, and we got product gas with about more than 80% hydrogen, and carbon dioxide more than 80%. So we can see that this product, this chemical looping, that can produce relatively rich of pure CO2 and pure H2, which is very important for synthesis reaction and sequestration. So next in plasma gasification. Plasma gasification is typically operated at very high temperature. The plasma and then gasify and melts the inorganic compound, which is very useful for processing municipal solid waste or hazardous waste. Now that we have seen all these different types of gasifier, so if I have to design a gasifier, let's say I need to design a gasifier of 75 megawatt thermal, and my feedstock is a coffee husk, for example. What type of gasifier would you use? Of the three types I mentioned. What would you use? Would you use entrained flow, or fluidized bed, or mixed bed? Yeah? Fluidized bed, that's good. And in fluidized bed, as you see that there are two types, right? Bobbling bed and circular fluidized bed. Which one would you use? I would use circular fluidized bed because capacity is a little higher. So these are the questions that we as a designer have to answer before we start the design. So So you can use this rough guide to choose what type you can use. First is the size consideration, and next is the type of fuel consideration, and then the gas use consideration. As I mentioned earlier, if you have to run a diesel engine in a small scale use, then downdraft gasifier would be ideal because it has the lowest torque concentration. But if I'm using some fuel with a lot of chlorine, for example, which causes agglomeration, caking, then I couldn't use any of the moving bed. Moving bed doesn't allow use of agglomerated material. It will just produce a huge chunk there. So these are the considerations which are used for selection of types. Next design steps is sorry about this. This is a specific throughput, kilogram per meter square per hour. As you can see, updraft has a less than 150, downdraft about 300, bubbling fluid is with 1500, dual fluid is with 10,000. And the last one is the different maximum size, 3 to 4 meter, downdraft, less than 1.5 meter, and fluid that doesn't have any limit. Now, what are the challenges for Balmer classification? That we need to understand to begin with. Availability is a major problem for all gasifiers. I know of many remote communities who were supplied with a gasifier to substitute use of fuel. Let me give a specific example. That there is in India, in the province of Bengal, near the sea, this is called Sundarban Delta. It's like the Amazon Delta. It's a thick, lush forest, and remote from any other place. It's very difficult, it could be impossible to carry electric cable to provide electricity there. So most of them, those small islands, they use diesel engine to run their generator. But diesel is expensive. So the government decided to offer them downdraft gasifier with a generator that they can run the same diesel engine. But unfortunately, that after few months, about more than 50% of the units were down. They went back to use of diesel because their availability is very low, and particularly unless they are not properly used. Complex unit operation is very important area. At one time there was a lot of discussion on the use of integrated gasification combined cycle (IGCC) for large-scale power generation, and that made a lot of sense. That you instead of burning the coal directly in the boiler to produce heat, if you gasify them and then burn them, then you, per unit electricity generated, you produce less pollutant and more green. But for those units, invariably used entrained flow gasifier. Entrained flow gasifier use pure oxygen. And where do you get oxygen? you have to produce oxygen. Oxygen plus coal gas. So oxygen has to come from the what we call oxygen separation unit, OSU. This is a very expensive unit to install as well as to operate. That comes with a lot of, because they liquefy air and separate oxygen and nitrogen. And as I said, it requires a large amount of auxiliary power. And when you design gasifier for biomass, you got to be careful that high alkali content of biomass. That creates agglomeration problem that I mentioned earlier. That is one of the major problems that we need to take a note of it. Now finally, the tar cleaning. Except for entrant flow on the extreme end and the downdrop is the lower end, all of them produce a lot of tar. And so cleaning of tar is a major issue that we need to consider before you move further. Finally, the very fact that gasification essentially is a reduction process, the inflation of carbon is very low. The carbon conversion efficiency is very low. If we get 95% plus, it's very high value. So all gasifiers come up with a large amount of unconverted char. So that is one of the features that you have to deal with, except for entrant flow gasifier. In entrant flow gasifier, it is a co-current reactor where the reaction medium and the reactant, they move together until reaction is complete. So the carbon conversion is very high. Okay, now we'll look into the theory of gasification. So I think at this point I will show you a small video that nicely explains the theory. Okay, let me see how I can go back to that. Okay, I have to start from here. Where did I have it here?
To explain what gasification is, how it works, and how industry uses this process. Gasification allows coal or even dry plants to be transformed into many useful everyday products in an environmentally friendly way by breaking down coal into molecular building blocks that can be reassembled primarily with oxygen and water to make plastic, clothing, gasoline, diesel fuel, fertilizer, and electricity. So, how does gasification happen? Let's start with fire, also called combustion. Wood, like coal, is mostly made up of carbon, hydrogen, and compounds that do not burn, called ash. Air is mostly oxygen and nitrogen. During combustion, oxygen bonds with the carbon and hydrogen, creating a chemical reaction that gives off so much heat that produces fire. The soft ash left behind would have to be carefully landfilled to prevent leaching of contaminants into the ground. Gasification is similar to fire or combustion, but it occurs in a closed vessel. Less air is provided than for combustion, and water is added as steam. Oxygen chemically reacts with the carbon in coal to become carbon monoxide. The hydrogen atoms in coal become hydrogen gas molecules. Water also provides oxygen to chemically react with carbon, leaving hydrogen behind. These chemical reactions give off heat, but less than if the coal were completely burned. The product of gasification is syngas, which is primarily carbon monoxide and hydrogen molecules. The sulfur in coal becomes hydrogen sulfide, which is separated from the syngas and is used to make sulfuric acid, which is then sold. Due to the high temperature inside the gasifier, slag is made instead of ash. Slag is like small rocks. Contaminants remain safely trapped inside, so slag can be used to make roads. Whereas gasification breaks coal down into small building blocks, other processes not covered here will reassemble these molecular building blocks, hydrogen and carbon monoxide, into all of these valuable products. To make clean energy from coal, we need hydrogen. To make more hydrogen, the water-gas shift reaction can be used to exchange each carbon monoxide molecule for a hydrogen molecule. When syngas is combined with steam in a catalyst, the water molecule gives off an oxygen atom to the carbon monoxide, turning carbon monoxide into carbon dioxide. Catalysts are used to increase the speed of chemical reactions. DOE's vision is to use hydrogen to generate electricity in a power plant with only water going up the stack. Coal can indeed be used to make clean electricity. But gasification is not limited to coal. Wood, natural gas, oil, and farm waste can all be burned to make heat. They can also be gasified to make clean electricity, clothing, fuel for cars, trucks, tanks and jets, and other products we use every day. Clean coal gasification can be done today. DOE is developing technologies to make this vision affordable. To learn more about these technologies and gasification in general, enter Gasifipedia into your preferred search engine.
Okay, so okay. Now, this is a schematic of an off-duct gasifier where fuel is coming from the top and oxygen, air and steam mixture is coming from water. So let me show the schematic here. Feedstock, gasification medium, and then product gas. Now, very top zone is receives the moist fuel. So naturally, the heat that comes with the product gas that is used to dry this biomass. So moisture leaves the area. Then when the dry biomass comes to the next zone, pyrolysis, where you have a dry field and there's no oxygen. So that undergoes cracking or depolymerization, devolatilization. The products, all the volatiles and char. The volatile matter, obviously, that leaves the chamber. That leaves the chamber, and then carbon or char that comes to gasification zone. And this is where all the gasification reaction, which is essentially endothermic reduction reaction, takes place. After that, any charge that which drops here, that undergoes combustion reaction, because here I'm adding oxygen or air, which comes in the contact with the hot carbon, immediately absorb all the carbon in exothermic combustion reaction that provide the heat. And that heat is utilized in the gasification zone to meet the demand of endothermic reaction. And that's why this is the temperature curve. This is the height and this temperature. As you can see, the temperature started rising from room temperature to about 950 in this case, or about 1000 degrees Celsius, at intersection with combustion gasification zone. And gasification being a endothermic reaction, this temperature started dropping, and then drops to 300 degrees Celsius or so. So that's a typical reaction. We have another more detailed reaction scheme. In the combustion zone, the reaction is primarily C plus O2 carbon dioxide, with H plus O2 steam, and here the volatiles, if any, that could burn to CO2 and H2O. And that heat is used partly in the gasification reaction, partly that goes into pyrolysis and drying. In gasification reaction, the primary reaction is C plus CO2 is 2CO. This is Buddha's reaction. Very famous reaction. Then next one, C plus H2O is CO plus H2. And then CO2 plus H2 is CO plus H2O. And this is the pyrolysis reaction. So they provide carbon monoxide and hydrogen. And combustion product provide CO2, carbon dioxide, and steam. Pyrolysis, CH4 and tar, dry only water. So the product gas is a mixture of all these components. So we have this is the reaction scheme. Can you please go to? I'm running low on the power. This is water to shift reaction. C plus H2, H2O is H2 plus CO plus 131 kilojoule per mole carbon. This is the endothermic gas which you need heat. Then Buddha's reaction that has CO2 plus C plus 2CO plus H2O. I do not know why they used, yeah, that's okay, all right, plus 172. Then the shift reaction, CO plus H2 plus CO2, H2 plus 42 kilojoule per mole. Then the methylation reaction, C plus 2H2 CH4. This is exothermic reaction, 75 kilojoule per mole. Partial combustion reaction, C plus 0.5 CO2 is CO minus 111. These last two reactions are exothermic reaction, and top three reaction are endothermic reaction. So whatever energy we need in this reaction had to be provided by these two reactions in gasification. And that's an important criterion for the design. So here's a calculation that shows how you can design a gasifier so that you don't need external energy to sustain the endothermic reaction. So we have this steam reforming reaction and then the partial oxygen reaction. And then you add them together, you could total reaction you can make 0, so that amount of oxygen which you provide is just sufficient to produce enough heat for this reaction. Now, good. Thank you. I'm all set. So here, so the way I design the gasifier is that I adjust the supply of oxygen to the gasifier only to the extent that we just supply the reaction heat needed for gasification. So that's how you design the gasifier. However, in reality, we need more than that. We have loss of heat. So accordingly, we trim the oxygen supply. Because if you apply more oxygen, then you will not only increase the temperature of product gas, you will also have more CO2 in the product gas, which is waste. Okay, now let me explain what I mentioned here. I wrote here gasification medium. What is gasification medium? Oxygen is a gasification medium, but not necessarily all the case. It could be steam, it could be air, it could be oxygen. Now, steam is important, but because it provides the hydrogen. Oxygen is important because it gives the combustion reaction. Air is something easily and inexpensively available, which can provide oxygen also. But the problem is the air has contained a lot of nitrogen, which has no purpose in the gasification. It simply dilutes the product gas. So if you wanted to have a very high heating value, then don't use oxygen, air. Use steam and oxygen, which is an expensive proposition. So in this context, the equivalence ratio is an important term which you use. It is the ratio of actual airflow ratio to the theoretical airflow ratio. That what is equivalence ratio. I'm sure that you can tell me as all familiar with that. So here, the ER value is typically for gasification between 0.2 to 0.3, whereas the combustion reaction is greater than 1. Now, if I go too low, then we have incomplete gasification, excess charge. If I go too high, then we have too much carbon dioxide, too much water and reduce heating hazard. So the best to thumb rule for design is to keep it within this range, 0.2 to 0.3. Here's a diagram that gives you carbon conversion efficiency as a functional equivalence ratio. As you can see that heating efficiency increases about 0.25, 0.23 and then start dropping. Now, question is, how do I go about designing it? In the combustion, I do the, you have the combustion student here, right? Okay. Those who are the thermodynamics combustion student, you are already familiar with how you calculate this stoichiometric calculation to find what the product gas or given feedstock and yeah. Similar reaction calculation we need to do for a gasifier, but it's more complex. There are two approaches for theoretical calculation. Is stoichiometric model and non-stoichiometric model. And this is essential basic fundamental design calculation for gasifier, which is independent of what gasifier type you use. But this involves a lot of assumptions. A, that we totally ignore car production, and we assume the chemical reaction infinite, and no heat and mass transfer resistance. Now, this calculation can give you a product that composition reaction calculation using chemical equilibrium calculation, one of those. But that's all theoretical. Best option, if you have access to experimental data, use that. So anyway, so this product gas prediction based on equilibrium calculation gives you tentative composition of flue gas, product gas. But there's another important aspect is energy balance. Because we have the different steps, gasification, combustion, pyrolysis, drying. So we define a boundary around the gasifier, take into account all this input output, and determine what the total energy demand, and that will help you find the total gasification efficiency. Now, to do this calculation, obviously you have to take some assumptions that how much of the charge is converted, how much heat is lost, and so on. But this energy balance is very important. The next important design parameter is gasification temperature. This is the single most important parameter which you will see even at the equilibrium calculation stage that determines the gasification efficiency and the product of gasification. Now, for example, if you want high hydrogen product, then you have to go high hydrogen. Next, the mass balance. Mass balance, once you have done these two steps, mass balance is relatively simple. You can do that mass balance based on the equilibrium calculation. Now, gasification efficiency. There are two definitions of gasification efficiency. One is cold gas efficiency, which is the heating value in the cool gas. That is only the chemical energy in the flue gas, in the product gas, over heating value of the fuel. But hot gas efficiency also takes into consideration the sensible heat in the product gas. For example, a product gas living at 800 degrees Celsius, it has a lot of sensible heat. So add that to it, so that will give you the hot gas efficiency. So any gasification, you've got to be careful the efficiency is given as coal gas efficiency or it is given in terms of hot gas efficiency. Okay, now we will examine the sizing or calculation of fluid-ended gasifier. In a fluid-ended gasifier, that cross-section area, very simple, we can design on the basis of fluid and velocity. So this is how we determine it. But one important parameter is bed depth. And for that, you need the optimum residence time of gas in the system, which is experimental value. And that experimental value has to be plugged in here to get the height of the bed. Freeboard, there is no definite means of calculating freeboard, but make sure that you have provide enough residence time for the charge conversion. And that's where charge is converted. So these are some of the steps that one would follow for gasifier design. Input, what are the flow feedstock, what are the medium, what are the design constraints, and what options we have. Then what is the expected performance, then sizing, configuration. We have already talked about this. These are the different steps in the process design. Input comprises fuel, gasification medium, equivalence ratio, product gas composition. Output, gasification configuration, size, operating parameter. These are typical values. I think I have shown this earlier. So I don't need to do it again. Next comes the design optimization. So design optimization that involves optimization that will give highest coal gas hot gas efficiency, least amount of unconverted charge and dark concentration, and attain required composition of gas and heating level of the product. Then engine optimization. Engine optimization will look at the capital cost equipment and operating cost, how to reduce those. Now, all these calculations that I've done so far were based on equilibrium calculation, assuming infinite reaction rate. But in reality, reaction rate takes place at finite rate. So determining that, we have to carry out the kinetic model studies. That essentially, that necessarily involve hydrodynamic model of the reactor, the reaction kinetic model, and appropriate heat and mass transfer model. So all these things added together give overall performance for a particular design. But what is very important, the experimental validation. If you don't have the experimental validation, then you have what you call validate input, validate output. So this is how we go about design of the gasifier. So I'll stop here and try to answer any questions that you might have on gasifier design.
Yo, pues lo más ¿dónde está Carlos? Que soy yo. El otro Carlos. Bueno, Carlos. Buenas tardes. En español mío he hecho cuatro. El profesor habla acerca de los parámetros influyentes en la gratificación. Luego hace una descripción donde muestra cómo ellos influyen en el diseño, cómo se requiere avanzar. Sin embargo, yo quisiera que él me dijera, cómo dentro de todas las tecnologías puede incluirse los efectos de la presión para poder generar un mejor diseño.
So, Professor, how take into account the old technologies, you can add the pressure parameter in affects the effects of the product.
O impacto al diseño.
Or in the design,
design,
of the gasifier.
How-
You mentioned the different technologies.
about the pressure.
The pressure when you have like a hydro or pressurized system, pressurized gasifier.
Now, the current model will tell you what impact it has. But my gut feeling is, in the chemical reaction, pressure may not have very large impact. However, that when in the current model, when we plug in partial pressure, then we might get a different values than what you get at full pressure. But you will pressurize the reactor only when you need a product gas which need to be pressurized. That's why a lot of intake for gasifier are pressurized because they need pressurized gas. But for most biomass gasifier used for small scale application, they don't need pressurized gas. So that's why they don't pressurize the reactor. But to answer your question, this equilibrium calculation will demonstrate the effect of pressure because that is based on the partial pressure.
Ahí es donde más.
Otra pregunta. Los de ingeniería de procesos.
Who
Mira el
else,
examen.
so who else is working in the gasification here? Can you raise your hand? Let me see who is working in gasification. Who is working in gasification? You?
Yes.
So you are professor. The professor is not counted.
Me too.
I will.
Carlo is going to work with
Wait,
Eventually.
I thought I did see somebody have a question on this.
I have a question. How affect the volume to the reduction zone in the quality of gas?
What is the effect of volume of?
Volume to the reduction zone.
Reduction zone. Okay. For a given reactor diameter, the height of the reduction zone is determined by the superficial gas velocity. So you don't necessarily create a reduction zone in the outdoor gasifier or in the gasifier. They automatically determine.
Otra pregunta.
Yes.
And what makes a cross-drop gasifier better for laboratory use over or what are the benefits of a cross-drop gasifier over a down-drop and a full-drop gasifier?
So outdoor gasifier, as I mentioned, is used in a large to medium industry. Down-drop gasifier used in a small application. So is that your question?
No. What are the benefits of a cross-drop?
So cross-drop
Over the full-drop and the down-drop?
Cross-drop sits in between these two, and I think that it was first developed in the Asian Institute of Technology in Bangkok to provide something in between. But I haven't seen that this application in much places.
I think it's too small
Yes.
size for the growth.
It's very difficult to scale up side vector.
Too small. Any question? Any more questions? Okay. Thank you so much. Nice presentation. No, ya no nos vemos sino dentro de un año. ¿Cómo? También lo podemos graduar. Mario, ¿tienes esta?
Sí, profesor.
Esta también. La pusiste ahí en la. Pero vea. Si quiere, no la semana que viene, la siguiente.
Whose is this?
Sí, y yo soy la estudiante.
I know many people do that.
Para contarle ya. Sí,
Dani, cierras, Dani, cierras pantalla cuando salgas, ¿sí? Cierras pantalla.